And as I said, this lecture probably will be Monday-ish before I actually get it up there, but it's exam 4 material, so there's no real problems there. Good, so let me also make sure that I have your class notes online. I want to make sure that I cover it all. Good, so as we've already covered another kind of organic derivatives of water, which was alcohols. And what I mean by organic derivatives of water is that we're going to replace, in the case of alcohols, one of the H's on water with a hydrocarbon group. If we did that same thing twice, then we would have ourselves an ether. So ethers can be thought of in shorthand as R1O, R2, where both of these are alkyl groups. They can be the same alkyl group or different, doesn't matter. Either way, you'll have an ether. But we do require that they both be alkyl groups, because if either one of those is a hydrogen, of course, you won't have an ether, you'll have an alcohol. So naming ethers is pretty straightforward. Probably one of the most commonly used ethers is this one here. This one's used all the time as a solvent. And as you might guess, you would just call that diethyl ether. And actually, people sometimes just call that ethyl ether too. So that kind of triggers me. I don't like that. And sometimes they even just call it plain ether because it's just the most commonly used ether. But diethyl ether is probably the most correct name. What if you had two different groups on there? Well, you might have something like, how about this? So I guess here we'll have, you've got isopropyl and cyclohexyl. I think cyclohexyl comes first. So I think the better name is cyclohexyl isopropyl ether. Or 2-propyl, that's fine too, but I hope OWL doesn't give you too much trouble. Someone always comes up with a version of the problem that's like 100 times more cruel than anything. Ethoxyethane. I mean, I see what you mean. There are names like that also. It's just that no one really calls that ethoxyethane. One common example that does use this, though, another really common solvent is dimethoxyethane, which looks like this. And don't worry, I'll write it down. Wait, CH2OCH3. And I guess if you really wanted to be picky, probably you should say that's 1,2-dimethoxyethane. So I would say if there's multiple oxygens, it is okay to use this type of nomenclature. You will sometimes find it that way. Remember, though, that in my exam, at least, it's multiple choice, so there should be one best answer, dimethoxyethane. That's another pretty commonly used ether solvent. Or while we're doing really common ones, this is another pretty commonly used ether solvent. This is sometimes called MTBE for methyl tert-butyl ether. However, remember how this works. Technically, the tert in tert-butyl doesn't count. We just use the B in butyl. B comes before M, so I think technically the best name is tert-butyl methyl ether. So if you've forgotten what a tert-butyl group is, please review that. That's something you'll need to know for the whole semester. Tert-butyl methyl ether. And this was used as a gasoline additive for quite some time. Tert-butyl methyl ether. So 3 separate words, tert-butyl, methyl, ether, 3 words. And that was used as a gasoline additive for a while to increase the octane rating. Turns out this stuff is un poco dangerous to the environment. It's un poco toxic. So now, as you're probably aware, the most commonly used gasoline additive is ethanol. So that's a lot cleaner and much more benign to the environment. But I think that gives you that gives you the bulk of the idea there in terms of naming ethers. I mean, there are certainly others that have their own names. I don't think I really care that you memorize too many of these trivial names. If I had to think of one other really commonly used ether solvent, it'd be this one, where the oxygen is contained in a 5-membered ring. That one we call tetrahydrofuran. And I'm not even going to write it down because I don't think I really care if you know that. But that's another pretty commonly used ether solvent. The reason it's called tetrahydrofuran is its name is based on this compound. That compound is called furan, F-U-R-A-N. And so if you add 4 hydrogens, tetrahydrofuran, you see the name makes sense. But before the reduced compound tetrahydrofuran is another pretty commonly used ether solvent. Between you, me, and the wall, if I'm doing a reaction in real life and I have a choice, I'm going to go for this guy. Diethyl ether is the easiest of all of them to use. And actually, I don't know if any of you are taking Chem 242 lab, but you may very well get to use diethyl ether at some point during the term. Maybe even the tetrahydrofuran, so the reduced version of that compound. You might get to use these. Don't snort up too much of this, although it smells very pleasant. Too much and you'll begin to feel a little bit woozy. It used to be used as an anesthetic. So, but you know, don't be huffing that stuff. Good. So I think that's about it for nomenclature. I've probably said a little too much. What else can I say about the properties of ethers? Oh, sulfides are the sulfur analog of ethers. So naming them is exactly the same as naming ethers. So if you change this oxygen to a sulfur, it'd be diethyl sulfide. You know, if you change this oxygen to a sulfur, tert-butyl methyl sulfide. It's the same to name sulfides as to name ethers. You just change the word ether to the word sulfide. So it's basically just adding ether at the end. Yes, but you have to name the alkyl groups that are on the ether. And technically you should go in alphabetical order. So I think cyclohexyl isopropyl ether is by far the better name here. But yes, you need, in general, you need the word ether. And I mean, there are other correct ways of naming these things. I think I just, oh, I see what I did. Okay, no problem. So yeah, there are other correct ways. You can see these alkoxy type names also, but I think I would certainly try this type of name first. I think that's by far the easier, more straightforward way to name them. Good. So, and again, I'm only looking at your class notes just to make sure I don't miss anything. Remember what we've said about hydrogen bonding. In order to be both a hydrogen bond donor and a hydrogen bond acceptor, you have to have an OH bond or an NH bond. Or another way of saying it, in order to be both a hydrogen bond donor and a hydrogen bond acceptor, the species must be protic. Well, ethers are not protic, even dimethyl ether, which is a thing. It's sometimes used for reactions that are done at very low temperatures, because dimethyl ether boils quite a bit below room temperature. I don't know exactly, but I think its boiling point is like -40 or -50, something like that. Might even be lower. So if you're doing a reaction at a very cold temperature, you can use this stuff and it'll be a liquid at that temperature. But as you can see, this compound's, and that's also, I should say, that's the smallest possible ether. I think you'll agree with me. You can't get a smaller ether than that. You need at least the 2 methyl groups and the oxygen in order to have an ether. And so, but this compound's not protic. There's no OH bonds. So it can accept hydrogen bonds using the lone pairs and oxygen. Remember, a hydrogen bond is not a covalent bond, right? We were pretty clear about that the other day. So it's not a covalent bond, but it can form one of those intermolecular non-bonding interactions. But you can't donate hydrogen bonds if the compound's not protic. So for that reason, actually that's a great example. I'll break my arm patting myself on the back. So dimethyl ether and ethanol are isomers, aren't they? They're both C2H6O. But I really should look up the boiling points. I've made myself curious at this point. I feel like ethanol boils at 78 or something like that. But we'll look it up. Of course, I don't care if you memorize this. Dimethyl ether boiling point. And there we go. Oh, that's so minus 24. And in that case, we'll also do ethanol. Wow, but that's Fahrenheit. I need it in Celsius. Oh, 78. Wow. That's why they pay me the big bucks right there. So did it say minus 12, I think, or something like that? It was below 0 anyway. But you can see that the difference is like 90 degrees here. So these two are otherwise, otherwise it's very much comparing apples to apples. Otherwise, it's a very fair comparison. They're isomers. They have the same molecular weight. But you've got hydrogen bonds in ethanol, both as a donor and as an acceptor, whereas diethyl ether could only ever act as a hydrogen bond acceptor. There's no way it can donate hydrogen bonds because it's not protic. And you can see the difference in boiling point is very dramatic. And so again, of course, I don't care if you remember that was lucky in my case that I have managed to have that memorized for the moment. But memorizing these numbers is not the point. But I think we can understand dramatic differences like that. Since we've got hydrogen bonding in ethanol, in order to get it to boil, you've got to put in a lot more energy in the form of heat. You've got to separate the molecules one from another and disrupt those hydrogen bonds. Again, remember, hydrogen bonds are not covalent bonds. When you boil something, you are not breaking covalent bonds. That's very important to know. I think that's almost, that should almost be common knowledge for someone who has a college education. That boiling is not a chemical change, it's a physical change. You're not breaking any covalent bonds. Anyway, so you see the difference there is pretty dramatic, and that's, I would say, almost strictly because of hydrogen bonding. So like I said, memorizing the boiling points, I don't really care if you do that, but that's something that I think we can understand. I've already pointed out how ethers are very commonly used as solvents. And again, the main reason is because they don't react with very many things. In fact, it's very hard to get ethers to react with much of anything. But I did want to pass along, I think this is the kind of practical knowledge that I can hand on to you guys. You do need to be careful with ether solvents. I don't know to what point you guys are going to be using them in the future, but you need to be careful. They're not something you want to leave sitting around for 6 months, at least not without taking certain precautions, because you can generate organic hydroperoxides. And what is an organic hydroperoxide? Well, it's something of this type. That's an organic hydroperoxide. And these things are kablam. These things are very, very explosive. Is Bronsted acid hydrogen donor or hydrogen bond donor? A Bronsted-Lowry acid is let's say a proton donor, but that's actually donating a hydrogen atom, a proton, H+. So that's different from hydrogen bonds. But yeah, that's a good point. Bronsted-Lowry acids are H+ donors. So these things are quite explosive. If they start to build up in any concentration, it's a very serious problem. Now, there are ways of testing for peroxides, and there are ways also of destroying peroxides, so they're no longer around. These have been around for decades and decades. But it's a problem when you're dealing with ether solvents. You need to make sure that you test regularly for peroxides, that you don't leave them unused for months and years, and that, if any peroxides, if you detect peroxides, you take care of that. But ether solvents are pretty dangerous in that regard. In such work as I do in a chemistry lab, I'm not a research professor here, but at least when there's not a global pandemic, I work over the summers for Dr. Daniel Singleton, who is a research professor. And I do some organic synthesis. I like to kind of keep my hands busy at least once a year doing that so I don't forget how. And my goodness, we go through these things, we go through these things by the gallon. Diethyl ether, you know, you don't have to worry about that stuff going unused in any standard chemistry lab. Good, so much for properties. How do we prepare ethers? I just want to, good. Yes, just wanted to make sure that I cover everything in your class notes. So there's two ways of making ethers. There's the old way, which is quite limited, and then there's the newer way, which is known as the Williamson ether synthesis, which is nothing other than an SN2 reaction. And that's the better of the two ways by far for making ethers. So I would say that the old way involves taking an alcohol, and this can be any aliphatic alcohol. So you don't want R to be a benzene ring, but any alkyl group is fine. And this will react in the presence of an acid catalyst. You generally need to heat it as well. Remember, triangle is shorthand for heat. But if you wanted to be picky in terms of getting a balanced equation, two of these alcohol molecules will react to give an ether. And you will also get a molecule of water as the side product. But the major organic product would be the ether. But this reaction is very limited. Maybe give this one a frowny face. It's a very limited reaction. First of all, it only works at all well when R is primary, when this is a primary alcohol. And in any case, you can only get symmetrical ethers, where the two R groups are the same. So it does work, but it's very limited. A much better type of method for, maybe not a frowny face. Let's just put an X here, because that's not a really great way of making an ether. It works, but it's not a very good way. A far better way is what's called the Williamson ether synthesis. And again, I'm less concerned that you know the name. Mr. Williamson might care, but I'm not so concerned about that. But that is what this reaction is called. And what do you know? I already demonstrated that. Do you need to use alcohol in excess amount? Well, there's only a catalytic amount of the acid. So you basically just drop a few drops of maybe sulfuric acid or something like that into nothing other than the alcohol. So yeah, and eventually the equilibrium will be such that you will get some of the ether. So I guess the one-word answer is yes, it's in excess, but it's also really the only organic reagent there. You just add a catalytic amount of the acid. So for H+, it might say H2SO4, it might say H3PO4. They might actually name an acid, but it doesn't really matter as long as you use just a little bit of some very strong, usually inorganic mineral type acid. But it's much better is to use the so-called Williamson ether synthesis. And we already know about this. This is nothing other than an SN1 reaction, such that we'll take some alkoxide ion, and we'll say in a few minutes about how to get that. But alkoxide ions are the conjugate bases of alcohols. They're what you get when you take off H+ from the alcohol R1OH. And we're going to react this with some alkyl halide, preferably primary. These work best if that's really the only limitation. But for best results, you want that alkyl halide to be primary, because this is nothing other than an SN2 reaction. And we've already said SN2 reactions work the best when the substrate is primary. Maybe secondary, you can get a little of it. Tertiary is right out. But that's really the only limitation. The limitation in the group R1 is pretty much none. You can use pretty much any group R1 you want to, but this is just going to give you an SN2 reaction. We can even write the mechanism. And yes, it does make that sound actually. If you put your ear up to the flask, you hear. I have to be careful because there's always someone, really? Yes, really. Jeez, they believe everything I say just because I have 3 letters after my name. I want you to take me seriously, but not that seriously. Geez. But you'll get, in this case, R2CH2OR1. So this portion here comes from your nucleophile, from your alkoxide ion. And that's basically it. It's just an SN2 reaction. You already know everything you need to know to understand the Williamson ether synthesis. And I will say also, if instead of an alkoxide, you use a thiolate ion, which is the same thing but with a sulfur, then you'll get a sulfide also. So you can make sulfides very easily this way too. That only leaves the question, how do you make these alkoxides? And there are a number of ways. There are bases that are strong enough to pull the proton off an alcohol for us. But there's another way to do it, and this is in the class notes too, that uses just an alkali metal, such as lithium or sodium or potassium. So here now, this is sodium metal. This is not Na+. This is elemental sodium. Yes, the stuff that makes a big explosion if you throw it into a lake. Apart from the obvious, please don't do that. It's so wasteful. It takes a lot of energy and money to make sodium metal from the cation. So please don't do that. But what you wind up getting is the alkoxide. It's actually a reduction reaction. And I'll show you why in just a moment. But that will give you the alkoxide ion. You'll, of course, also have Na+. So the sodium is actually oxidized. It goes from an oxidation number of 0, right? You recall from your Gen Chem, all pure elements have an oxidation number of 0. So this goes from 0 to +1. So the sodium is oxidized. And the other thing you will also get is, at least the way I've done the stoichiometry here, half a mole of hydrogen gas. So that's where the fire comes from, right? Hydrogen is very, very flammable. And so now I know some Gen Chem professors don't like fractional coefficients. I think they're fine. I see nothing wrong with an occasional simple fraction like that. But if you wanted to say 2R1OH plus 2Na gives 2 of these, 2 sodium ions and H2 gas, that's fine. I don't care which way you do that. But this is essentially a redox reaction. The sodium is oxidized from 0 to +1, and the hydrogen is reduced from +1 to 0, right? That's elemental hydrogen. So the oxidation number is 0. And that bubbles out, and you get a solution of your alkoxide as the sodium salt. So that's one of the more common ways of doing it. So if you wanted to do one of these things, you take your alcohol, R1OH, again, R1 can be pretty well anything. We'll do an example in a moment, of course. And you'll treat it with some alkyl halide, preferably primary. For example, let's make methyl tert-butyl ether. The way I would do it is I would take tert-butyl alcohol. The first thing I would treat it with is sodium metal, or lithium or potassium metal, doesn't matter which. And that will give us the alkoxide. And you can write Na+ or not as you choose. Watch OWL carefully though, because they might actually want you to put in another sketcher and put Na+ in it. They're really weird like that sometimes. And then for our second step, we would simply treat this with methyl iodide. CH3, I, and yes, if you put CH3Br or CH3Cl, I would accept it. Anyway, your exam is going to be multiple choice. But in real life, we like to use methyl iodide because methyl iodide is a liquid at room temperature, and the others are both gases. So liquids are easier to measure out. But in any case, you get an SN2 reaction, especially with this being a methyl or primary substrate, and you'll get methyl tert-butyl ether. So in order to get the right answer, you just look at your alkoxide, or if you will, look at the alcohol and imagine losing the proton from the alcohol, and then you look at what's attached to your halogen, and you just connect whatever is attached to the halogen to this oxygen, and you'll get the right product. And that's going on YouTube. You can watch me saying that as many times as you like. Incredibly, I'm pretty much out of time, but I think that was basically it. We're going to skip most of the material. I mentioned this already about MTBE. I guess I would like you to be aware of what an epoxide is. I think we've mentioned this before, but it bears repeating. Epoxides are three-membered cyclic ethers. So that compound by itself is just ethylene oxide. There, of course, are 4 bonds here, 2 to each carbon, and those can be to whatever you like. They can be to alkyl groups or whatever. So you can have substituted epoxides also. As you can imagine, a very, very strained compound, right? 3-membered rings are very, very strained with what we call angle strain. Because if you work it out, this angle here has to be 60 degrees. But all 3 of our atoms, our 2 carbon atoms and our oxygen, are sp3 hybridized. The way I know that is there's only single bonds here. So they don't want to be 60 degrees. They want to be 109.5 degrees. So maybe here's a good spot for a frowny face. It's very unhappy having the angles compressed so far away from 109.5. So there's lots of ways that you can do SN2 reactions on this guy and break open the 3-membered ring. And in doing so, it releases a lot of energy. You won't be responsible for any of that, and I put that in the class notes. But I guess I would like you guys to be aware of what an epoxide is. It's a 3-membered cyclic ether. And they're very, very reactive, unlike all of your other ethers, which are pretty unreactive.